Thank you all. I am Richard Lewis from the University of Sheffield, and today I'm presenting as titled. The purpose of this research is to provide an efficient tool for the design engineer concerned with assessing engineering components experiencing Mode 1 loading. So, to start with, my presentations will follow the following order, with an introduction, a hypothesis, methodology, results, and solutions. So, to start with, an introduction. State of the art, as many of these presentations have shown over the last couple of days, the theory of critical distance is very accurate in predicting failure in notched components, typically within error results of about plus or minus 20%. So the theory of critical distance owes its origins to the pioneering work done by Nuber and Peterson back in the 1930s, and over the last 80 odd years or so it's been discovered, rediscovered and applied to various different applications in various different engineering fields. The theory of critical distances can be formalised into four main methods, which are the point method, the line method, the error method and the volume method. The point method, the common feature within all of these methods is that they assess the elastic stress field ahead of a stress concentration feature using the critical distance. And the components are assumed to fail when the stress at the critical distance reaches material strength. The critical distance can be formalised mathematically using this formula, as we've seen in previous presentations, making it a function of the plane strain fracture toughness and strength. Today I'm only going to be using the point method, and so to just go into a little bit of detail about that, in the conventional setup of the point method, the critical distance and the inherent strength, sigma naught, determined experimentally by testing two light samples containing two very different notches, a sharp V notch and a blunt U notch. By plotting the failure curves ahead of the stress concentration feature, at the point in which the lines cross coincides to L/2 and sigma naught, as in the point method. So this leads me on to the fact that the theory of critical distance, as I said, very accurate. So what's the problem? The problem is that the theory of critical distances generally requires experimental validation, or experimental verification of the critical distance and the material's inherent strength. Through research, the inherent strength has seen the the inherent strength take the value of the UTS when the material is very brittle. And when the material stops being brittle, becomes quasi-brittle, ductile, the inherent strength is seen to be larger, which fundamentally means that it cannot design a plain specimen as it would be produced very large, non-conservative errors. Simply identifying the difference between a blunt notch and a sharp notch, blunt notch, and plain Sanford transition. So, in this simplified engineering approach, I plan to set the material's inherent strength to the material's UTS throughout all materials to see what happens. But this obviously raises this simple question that does the TCD still work in this scenario? Now, the only way to answer this is by validation. So, the main bulk of this work is by validating this method. And to do so, I've compiled a data set made up of over 200 Mode 1 test data results taken from technical literature, of which many of these are actually representative of maybe 3 or 5 experimental results. So, the compiled data, obviously I've included the mechanical behaviour, different types of materials, a variety of notches and stress concentration features, various different test types, but most importantly I've recorded the UTS and fracture toughness so that I can calculate LE, and I've also included the taken down the geometry, as the geometry is very important. So, to move on to the, I didn't point out earlier, TCD requires two components to be able to be used. It needs the two material parameters and it needs an accurate stress field. So I've performed finite element analysis on the different models using the above assumptions. This is a typical example of a model that I've produced, and as you can see around the notch apex, the mesh density is refined. And it's refined to a point where the stress, in this case it's the maximum principal stress, is converged at the critical distance. So, once I've determined the failure stress using the failure stress at the critical distance, I need to calculate an error. So, if we consider the UTS to be the design strength at the critical distance, if the validation stress is higher, then the material is stronger, therefore the result is conservative. And vice versa, if it's less, it's not conservative. So, to move on to the results of the analysis, initially the maximum principal stress was extracted from the finite element analysis as it's coincident with the maximum opening stress under mobile loading. So, moving through the results, you can see that we have brittle, quasi-brittle and ductile materials. With a mean error of 30%, which is good, and as you can see, as the materials become more ductile, the scatter appears to increase and also the non-conservative error increases. But the important point from a design engineering point of view is a safe design, and the non-conservative errors don't exceed -27%. To counteract the apparent increase in scatter and conservative, von Mises stresses were used to as the assessment stress, which resulted in less scatter but slightly more non-conservative results. Using the maximum principal stress results, I've plotted them on a dimensionless abscisor, which is a ratio of the notch root radius and the critical distance, since the critical distance is a measure of how sensitive the material is to defects or notches, and the notch root radius is considered to be the most important factor in the geometrical stress concentration picture. And as you can see, it's irrelevant, regardless of the ratio, the results are quite uniformly banded throughout, so with a few outliers. By plotting the error results on a cumulative probability distribution, it makes it quite easy to see that in the very bottom left side, there is only a small percentage of the maximum principal stress error results on the non-conservative side, with less than 2% exceeding 20%, or -20%. And the von Mises stresses plotted in this show that it does decrease the scatter, however there is an increase in non-conservatism. So to move on to some conclusions, using the maximum principal stress in this type of analysis means that a design safety factor of at least 1.2 could be implemented. And if the material is quasi-brittle, semi-ductile, ductile, and von Mises stress is used, then a safety factor of at least 1.5 should be used. And finally, further work is required to expand this engineering approach to the mixed mode case, which I am now currently working on. And as a slight final thing, I'd also like to acknowledge my industrial partner, Safe Technology Limited. And also, thank you all very much for your attention.